From 1983 Linguistics AI to 2026 Medical AI, number 1563, the 7th of March 2026, Gerald C. EclaireMD Foundation, category, Artificial Intelligence and Personal Innovation. Preface. This paper explains how for decades of my personal experience, from early linguistics AI in 1983 to modern medical AI applications in 2026, reveal the fundamental difference between human and machine reasoning, and how integrating both forms of intelligence now shapes my daily medical research work. Introduction. Looking back over my long experience working with artificial intelligence writing systems, I gradually discovered a consistent pattern. Modern AI can produce very clean and grammatically correct sentences. The structure is logical. The paragraphs flow smoothly, and the final result often looks polished and elegant. However, I also noticed something important. AI frequently removes or omits the concrete examples that explain and prove the idea behind a sentence. In other words, the writing may look beautiful but sometimes lacks the substance or supporting evidence that gives the statement real meaning. Without specific examples, the explanation can sound polished but abstract, hollow, or unreal. Much like a politician's speech, the logic may be present with beautiful words and phrases, but the necessary proof is missing. Working with AI-prepared writing pieces sometimes makes me wonder whether my own writing is too heavily influenced by engineering or scientific thinking and training. Over time, I began to describe this phenomenon as the example gap, or what might also be called the abstraction trap. I tend to compress explanations into elegant summaries while removing the specific examples that give ideas their physical meaning. This observation did not appear suddenly. It emerged gradually through decades of thinking about language, engineering, and computation. In many ways, it connects directly to an experience from more than 40 years ago. Engineering thinking, idea, example, mechanism, implication. My own thinking process follows a different structure because of my training in mathematics, physics, and engineering. I naturally explain ideas through concrete examples, solid numbers, and observable mechanisms. In engineering, an idea is rarely presented alone. It is normally followed by an example, a measurement, a figure, or a physical explanation. The structure often follows a simple pattern: idea greater than example, mechanism greater than implication. An idea becomes meaningful only when supported by real observations. For example, when discussing blood pressure signals, I might explain that blood pressure behaves like a waveform. I then immediately give examples. Blood pressure oscillates with each heartbeat, changes with respiration, and varies across circadian cycles throughout the day. These examples are not decorative language. They are evidence showing that the concept is real. When AI removes these examples in order to simplify a sentence, the explanation becomes weaker even though the grammar may look technically better. It took me some time to recognize this fundamental difference between human reasoning, natural intelligence, or NI, and machine language generation, artificial intelligence, or AI. This observation and realization reminded me of a real entrepreneurial experience from my early career. The 1983 Stanford University experience. Around 1983, I was working with a linguistics professor at Stanford University. At that time, we attempted to build a computer system capable of processing human language, something conceptually similar to what systems like chat do today. More than 40 years later, our goal was to combine linguistic understanding with computer algorithms so that machines could generate meaningful human language. However, our innovative idea and effort in 1983 ultimately failed. Our idea was early, actually ahead of its time, but the required computing resources were not available. Looking back now, the reason is very clear. The computing technology and intellectual environment at that time were simply not ready for such an advanced idea and system more than 40 years ago now. As I have become a frequent user of today's available commercial AI tools, I finally realize how advanced my thinking was at age 36 in Silicon Valley. 3 essential conditions required for modern AI simply did not exist in 1983. First, computing hardware power was extremely limited. The computers of the early 1980s simply did not have the processing capacity required to analyze complex language patterns, nor did they have sufficient data storage capacity in memory or hard disks. Today, this limitation has largely disappeared with the availability of cloud-scale GPU computing. My previous work experience at Sun Microsystems, which allows massive neural networks to be trained and deployed across distributed computational systems. Second, large language datasets and supporting software did not exist. Modern AI systems are trained on billions of sentences from books, articles, and the internet, forming internet-scale language corpora that provide the statistical foundation for machine learning models. In 1983, this type of data infrastructure was simply not available. Third, and perhaps most important, there was a significant interdisciplinary gap between linguistics and electronic engineering. At that time, linguistics was primarily focused on grammar theory and sentence structures, while engineering and computer science were focused on algorithms, logic systems, and computational efficiency. These two disciplines approached language from very different perspectives. Because of this gap, it was extremely difficult to translate linguistic theory into working computational systems. The worlds of linguistics and engineering were moving in parallel but rarely intersected. Linguists were studying the structure of language, while engineers were building computational machines. Yet there was little practical bridge between these two domains. Today, this gap has been largely bridged through interdisciplinary programs that combine computer science, linguistics, and machine learning, allowing researchers to integrate language theory with computational modeling. Looking back from today's perspective, it is clear that the eventual success of modern AI required the integration of these disciplines along with advances in computing power, large-scale data, and new mathematical approaches. What seemed impossible in 1983 gradually became achievable only for decades later when these technological and intellectual conditions finally converged. Interestingly, the development trajectory of AI is highly similar to my present medical research approach, where I integrate mathematics, physics, engineering, physiology, and pathology to study complex biomedical systems. Nevertheless, I am still proud of myself for having such forward-thinking and innovative ideas based on my mid-engineering training back in 1983. More than 40 years before OpenAI announced its chat product in early 2024, the same Silicon Valley location, but different innovators at a much later time. Modern AI and the engineering shift. Interestingly, modern AI systems did not emerge primarily from classical linguistic theory. Instead, they evolved from statistical learning, pattern recognition, and large-scale neural network computation. In other words, the field gradually moved closer to mathematics, engineering, and signal processing rather than traditional linguistic theory. Language began to be treated more like a complex signal rather than a set of rigid grammatical rules. Massive datasets allowed algorithms to detect statistical patterns across billions of sentences. This shift represents a fundamental transition from rule-based language theory toward data-driven pattern recognition. When I look back at the 1983 effort today, I realize that the idea itself was not wrong. It was simply ahead of the available technology and infrastructure. The vision was correct, but the era was not yet ready. Natural intelligence and artificial intelligence. Today, when I work with AI systems in my medical research and paper writing, I see a complementary relationship between natural intelligence and artificial intelligence. These two forms of intelligence operate in fundamentally different ways. Natural intelligence, represented by the human brain, works through associative and parallel processing. When I observe a dataset, multiple related ideas may appear almost simultaneously. Concepts from engineering, physiology, mathematics, and system analysis may suddenly connect together. This is what I sometimes describe as the neuron way of thinking. Ideas appear in clusters and can jump rapidly between disciplines. Artificial intelligence works differently. AI algorithms organize information sequentially. They construct sentences step by step, number by number, and equation by equation. This can be described as the computer way of thinking. I have watched chat prepare a graphic figure using my dataset. It operates digit by digit, equation by equation, and step by step like a beginning high school student, but with ultra-fast speed. Modern AI systems operate on massive computational infrastructures with multiple CPUs and large memory capacity. Their ability to store and process large amounts of information is extremely powerful. However, they still lack intuitive pattern recognition, what human minds often call the sixth sense or intuition, and the spontaneous connections of ideas that characterize human creativity. Human intelligence can jump between distant concepts and automatically, or subconsciously, connect them. These rapid conceptual leaps often become the source of scientific discovery and innovation. Among human beings, this differentiates idea innovators from rule-following engineers. The collaboration between me and AI. Today, my medical research process has become a collaboration between these two forms of intelligence. Natural intelligence generates ideas through pattern recognition, cross-disciplinary connections, content structuring, mechanistic thinking, and insight extraction from research outputs. Artificial intelligence helps organize my ideas into structured explanations that can be communicated clearly to readers. In many ways, commercial AI tools have become my most efficient research assistants. Years ago, around 2010, I hired a medical doctor to work as my research assistant at a salary of about $200,000 per year. Today, I pay roughly $240 per year, $20 per month for AI subscription services. The difference in cost is remarkable. Of course, a human assistant could discuss ideas with me and participate in intellectual exploration. However, idea generation is something I am comfortable doing myself. What I truly need assistance with is the more mechanical and labor-intensive part of research work, such as organizing data, preparing figures and graphs, and helping structure written explanations. In these areas, modern AI tools are extremely efficient. In practice, this collaboration has become part of my daily medical research routine. My brain often generates ideas quickly, especially during quiet morning or nighttime hours. Multiple concepts may appear at the same time before I have an opportunity to write them down. To capture these ideas, I often save important thoughts as keywords in notes or copy my conversations with AI systems into Word files on my iPhone. This allows me to preserve the raw ideas immediately before they disappear from memory. The following day, those captured ideas become the foundation for my structured writing. Natural intelligence generates and connects the key ideas, while artificial intelligence helps organize those ideas into clear written articles. And this way, I utilize the strengths of both. In simple terms, my daily research process follows 4 steps. 1. Idea generation and conceptual structure through natural intelligence. 2. Idea capture through recorded conversations and keyword notes. 3. Idea organization, sentence expansion, and fact verification through AI assistance. 4. Knowledge production through completed written articles created by Theny plus AI model. This workflow reflects a continuous cycle between human creativity and machine-assisted efficiency. 4 decades later, ironically, this process is very similar to what a Stanford linguistics professor and I attempted to achieve 41 years ago at Stanford University in Silicon Valley. The difference today is that the technology, especially since 2024, has finally caught up with the original idea we had in 1983. Over these 4 decades, I have transitioned from a middle-aged entrepreneur through serving as the CEO of a successful semiconductor AI algorithm-based chip design company to a senior medical research scientist. Instead of trying to build such a system from scratch, I now use these AI systems as research tools that assist my medical research process. Natural intelligence generates ideas and recognizes patterns, while artificial intelligence organizes those insights into structured communication documents. In a sense, the vision that seemed impossible in 1983 has finally become practical in 2026. Over these 4 decades, I have gone from being a grandfather of early ideas to becoming a grandson of modern AI usage. The original idea did not fail, it simply had to wait for the world to catch up. Looking forward, the next stage of artificial intelligence may involve systems that not only generate elegant abstractions but also preserve the concrete examples that give ideas their true meaning. When that happens, the gap between human reasoning and machine language may become even smaller. Epilogue. My pattern recognition capability has been the major reason for my success across 6 decades in academics, professional work, high-tech entrepreneurship, and medical research. Disclaimer: I write this paper not for fame, but to share what I have learned so others can understand their health, prevent disease, and live longer, healthier lives. This content is provided for educational reference only and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C. This content is provided for educational reference only and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C.